Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello everyone, and welcome to our discussion on the intersection of machine learning and mixed integer programming, MIP. Today, we're fortunate to have the opportunity to delve into the technical details of this exciting field with an expert in the area. To begin, could you please provide us with an overview of the motivations behind using machine learning to solve MIP problems?
Sure. I'd be happy to provide an overview of the motivations behind using machine learning to solve MIP problems. MIPs are a powerful tool for solving a wide range of optimization problems, but they can be very difficult to solve, especially for large or complex problems. Traditional methods for solving MIPs, such as branch and bound, can be computationally expensive. Machine learning offers a number of potential advantages for solving MIPs, including faster computation. Machine learning models can be trained to solve MIPs much faster than traditional methods. This is because machine learning models can learn from historical data to identify patterns and make predictions, which can be used to guide the search for a solution. Improved accuracy. Machine learning models can also be more accurate than traditional methods. This is because machine learning models can learn from a large amount of data, which can help them to identify complex relationships and patterns that traditional methods may miss. Flexibility. Machine learning models can be adapted to solve a wide range of MIP problems. This is because machine learning models can be trained on different types of data and can be customized to meet the specific requirements of a particular problem. Overall, machine learning offers a number of potential advantages for solving MIP problems. As a result, there is a growing interest in using machine learning to solve MIPs, and a number of promising results have been achieved in recent years.
Excellent. Thank you for providing that overview. Next, I'm curious about the different ways in which machine learning can be integrated with MIP solvers. Can you describe the main categories of ML-based MIP solvers and provide examples of how they are used? Additionally, I'm interested to know how ML techniques have been successfully applied to enhance MIP solvers and the benefits that have been observed.
Machine learning ML techniques are applied to enhance MIP solvers in several ways, resulting in significant benefits. 1. Improved heuristic algorithms. ML can enhance heuristic algorithms, which are designed to find approximate solutions to MIPs. By training ML models on historical data or problem features, these algorithms can make more informed decisions and explore promising regions of the solution space more efficiently. 2. Smarter branch and bound decisions. ML techniques can assist in making wiser decisions within the branch and bound algorithm, which is a widely used exact method for solving MIPs. ML models can predict the difficulty of subproblems, guide the branching strategy, and identify promising nodes to explore, leading to faster convergence to optimal solutions. 3. Enhanced cutting plane generation. Cutting planes are constraints that tighten the relaxation of the MIP and can significantly reduce the solution space. Unsupervised. ML models can be employed to identify effective cutting planes, which can be added to the formulation to accelerate the convergence of the solver. 4. Efficient initialization. ML techniques can be used to generate high-quality initial solutions for MIPs type. By leveraging historical data or problem characteristics, ML models can provide good starting points for the solver, reducing the computation time required to reach optimal or near-optimal solutions. 5. Solver parameter tuning. ML models can assist in optimizing the parameters of MIP solvers, such as the branching strategy, node selection criteria, and cutting plane generation frequency. By tuning these parameters based on problem characteristics or historical data, ML can improve the overall performance and efficiency of the solver.
Thank you for providing those insights into the integration of ML with MIP solvers. I'm particularly interested in the specific ML techniques that have been successfully applied in this context. Can you provide some examples of these techniques and explain how they have been used to enhance MIP solvers? Furthermore, I would like to know how the integration of ML has impacted the performance of MIP solvers in terms of solution quality, computation time, and scalability to larger and more complex problems.
Machine learning techniques that have been successfully applied to enhance MIP solvers include 1. Reinforcement learning. This technique has been used to train agents that can learn to make good decisions in the context of MIP problems. For example, the ICO-DQN framework redesigns the action space of the reinforcement learning agent, which allows revoking the previous action. In other words, the action of the agent is revocable in the ICO-DQN framework. 2. Supervised learning. This technique has been used to train models that can predict the optimal solution to a MIP problem. For example, the GN model has been used to predict the solution value for variables in a MIP problem. 3. Unsupervised learning. This technique has been used to identify patterns in data that can be used to improve the performance of MIP solvers. For example, the NN model has been used as a warm start for MIP solvers.
Thank you for providing those examples of ML techniques used in MIP solvers. I'm also interested in the practical implications of integrating ML with MIP solvers. Can you describe the benefits that have been observed in terms of solution quality, computation time, and scalability to larger and more complex problems? Additionally, I'm curious about the challenges and limitations of using ML to enhance MIP solvers. Are there any specific problem types or scenarios where ML-based approaches may not be as effective?
Machine learning, ML, can be used to enhance MIP solvers in several ways. 1. Predicting solution quality. ML models can be trained to predict the quality of solutions obtained by MIP solvers. This information can be used to guide the search process, focusing on promising areas and avoiding unnecessary computations. 2. Selecting branching strategies. ML models can be used to select the most effective branching strategies for a given MIP instance. This can help to reduce the number of nodes in the search tree and speed up the solution process. 3. Generating high-quality initial solutions. ML models can be used to generate high-quality initial solutions for MIP solvers. This can help to reduce the amount of time required to find a feasible solution and improve the overall solution quality. 4. Identifying redundant constraints. ML models can be used to identify redundant constraints in MIP instances. These constraints can be removed to reduce the size of the problem and speed up the solution process. 5. Adapting solver parameters. ML models can be used to adapt the parameters of MIP solvers to the specific characteristics of a given instance. This can help to improve the performance of the solver and obtain better solutions.
Thank you for providing those insights into the benefits of using ML to enhance MIP solvers. I'm curious to know if there are any specific problem types or scenarios where ML-based approaches may not be as effective. Are there certain characteristics of MIP instances that make them less suited for ML-based enhancements? Additionally, I'm interested to learn about the potential limitations of ML-based approaches in terms of scalability and computational complexity. Are there any practical considerations or constraints that limit the applicability of ML-based MIP solvers to large-scale or complex problems?
Yes, there are certain problem types or scenarios that affect the effectiveness of ML-based MIP solvers. For example, the effectiveness of ML-based MIP solvers can be affected by the problem size, the structure of the problem, and the availability of high-quality training data. In general, ML-based MIP solvers are more effective for solving smaller problems with a well-defined structure. Additionally, the availability of high-quality training data is crucial for training effective ML models.
Thank you for clarifying the factors that affect the effectiveness of ML-based MIP solvers. I'm interested to know more about the challenges and limitations of using ML to enhance MIP solvers. Are there any specific computational or algorithmic hurdles that need to be overcome? Additionally, I'm curious about the potential trade-offs involved in using ML-based MIP solvers. For example, are there any situations where the use of ML may introduce additional computational overhead or compromise the optimality guarantees of the solution?
There are several challenges and limitations when using ML to enhance MIP solvers. Data availability. Training ML models requires a large amount of data, which may not always be available for MIP problems. Collecting and preparing data for MIP can be time-consuming and expensive. Model interpretability. ML models can be complex and difficult to interpret, making it challenging to understand how they make decisions. This lack of interpretability can make it difficult to trust the results of ML-enhanced MIP solvers. Computational cost. Training ML models can be computationally expensive, especially for large-scale MIP problems. This can make it difficult to use ML techniques in practice, especially for time-sensitive applications. Generalization. ML models are only as good as the data they are trained on. If the training data does not represent the full range of MIP problems that the solver will encounter, the model may not generalize well to new problems.
Thank you for outlining the challenges and limitations associated with using ML to enhance MIP solvers. I am particularly interested in the potential trade-offs involved in using ML-based MIP solvers. Could you elaborate on the situations where the use of ML may introduce additional computational overhead or compromise the optimality guarantees of the solution? Additionally, I'm curious to know if there are any ongoing research efforts or promising directions to address these challenges and limitations. Are there any advancements or techniques that show promise in overcoming these hurdles and improving the effectiveness of ML-based MIP solvers?
Sure, here is a detailed explanation of the additional computing overhead and the potential decrease in solution optimality that can occur when using ML-based MIP solvers. Additional computing overhead. ML-based MIP solvers often require additional computing resources compared to traditional MIP solvers. This is because ML models need to be trained on large datasets, which can be computationally expensive. Additionally, ML models can be complex and require specialized hardware, such as GPUs, to run efficiently. Potential decrease in solution optimality. ML-based MIP solvers may not always find the optimal solution to a given problem. This is because ML models are not perfect and can make mistakes. Additionally, ML models are often trained on a limited dataset, which may not be representative of all possible problem instances. How to mitigate these issues? There are several ways to mitigate the additional computing overhead and potential decrease in solution optimality when using ML-based MIP solvers. Use efficient ML models. Choose ML models that are designed to be efficient and can be trained quickly. Use specialized hardware. Use GPUs or other specialized hardware to speed up the training and execution of ML models. Use a representative dataset. Train ML models on a dataset that is representative of all possible problem instances. Validate the results. Validate the solutions found by ML-based MIP solvers using other methods, such as traditional MIP solvers. Overall, ML-based MIP solvers are a promising new approach to solving MIPs. However, it is important to be aware of the potential additional computing overhead and decrease in solution optimality that can occur when using these solvers. By carefully considering these factors and taking steps to mitigate them, you can use ML-based MIP solvers to solve complex MIPs quickly and efficiently.
Thank you all for joining us today. We hope you found this discussion on the integration of machine learning into mixed integer programming solvers informative and thought-provoking. As we've learned, machine learning offers significant advantages for solving MIP problems, including faster computation, improved accuracy, and enhanced flexibility. Now techniques can boost MIP solver performance by optimizing heuristic algorithms, making smarter branch and bound decisions, and generating more effective cutting planes. We've also explored the challenges and limitations of ML-based MIP solvers, such as data availability, model interpretability, computational cost, and generalization. Ongoing research aims to overcome these challenges and improve the efficiency and effectiveness of ML-based solvers. We encourage you to continue exploring this exciting field and stay updated on the latest developments. Remember, the integration of machine learning into MIP solvers is still in its early stages, but it holds tremendous potential for revolutionizing the way we solve complex optimization problems. Thank you again for being here. We appreciate your participation and look forward to future discussions on the cutting edge of technical innovation.